All right, class. I'm really sorry for the delay. Um,
Hey, be quiet, Bug! Be quiet! Be quiet! Knock it off! Hey! Hey!
Gosh darn it. Bug is outside in the backyard, and he's been having just a great time barking at all the people who are walking around. Because I don't know about your neighborhood, but my neighborhood, everyone is walking around all the time. Um, so, Bug has lots to bark at. Sorry for the delay. My router, needed to be restarted 5 times in a row. But now I seem to have a stable internet.
Bug, knock it off!
Couple things here. First of all, I'm going to be writing my answers today, so this should be a little bit easier. Second thing I wanted to say is you guys were supposed to have done the 2004 free response questions yesterday. And guess what? Guess what year I graduated from high school? 2004. And so you guys, if you did the daily item yesterday, then you did the exact same AP Physics C free response that I did when I took the AP Physics C exam. So I got a 5. Did you get a 5? Based on your performance, that's my question for you. Next thing I wanted to say is I bought some important items this morning. I got critical items that I'm purchasing. I purchased a throwing axe. I purchased some Crocs. I purchased, what else did I get? Goo for running. So if you're running, you take this, if you're doing long distance runs, you're on mile 15, you're exhausted. There's these little packets, and it's like pudding, and you just take the packet and you squirt pudding into your mouth. It's disgusting, but it gives you energy. And I also got the board game Dominion, which I've heard is excellent. So I'm thinking I'm going to buy a knife forge. It's something I've wanted to do for a long time, and I think I'm going to do it. I got my stimulus check. I'm going to waste it on getting knife making tools. It should be interesting. So maybe I'll send some pictures on my knives that I make. All right, so let's get into the physics. What do we have here? We've got, consider the electric field diagram above. Points A, B, and C are all located at y equals 0.06 meters. At which of these 3 points is the magnitude of the electric field the greatest? Justify your answer. Well, one of the things I taught you, so these are the electric field lines. And one of the things I taught you is that the electric field is largest at points where the field lines are close together. So between A, B, and C, so this is number 1, part A, I. So I would say that the electric field is strongest at point C. For part 2, it says at which of these 3 points is the electric potential the greatest? And you get a bigger electric potential by Miles asks, have you played Settlers of Catan? And the answer is yes, I have played it. I own Settlers of Catan as well. Has anyone played Dominion? I don't know. If you played Dominion, let me know. Oh, hey, Ruby. Nice to see you. Or I'm not seeing you, but nice to have you present as well as everyone else. All right. So we're on part 2. And for part 2, we want to know which of the 3 points is the electric potential the greatest. And you want to think about electric potential. You kind of want to go, to get the highest potential, you want to go uphill. So you want to go against the electric field lines as far as possible. And so we can see that going uphill against the electric field lines would take us to the left. And so point A is going to have the greatest electric potential. All right. Part B says an electron is released from rest at point B. Qualitatively describe the electron's motion in terms of direction, speed, and acceleration. So electrons, they go against the electric field because they have negative charge. So it's going to accelerate to the left. So I would say accelerates left.
Knock it off, Bug!
But as it goes left, the electric field weakens because the field lines are getting farther apart. So I would say the acceleration goes down as it moves left. Okay. Now it says calculate the electron's speed after it has moved through a potential difference of 10 volts. Well, one of the things I taught you is that energy is conserved. Initial energy equals final energy. And the initial energy is going to be 1/2 mv initial squared, which is 0, plus Q times the initial potential, which is also 0. So initially the electron has 0 energy. Afterwards it has, well, we could say it starts off with 10 volts. Let's just say it starts off with 10 volts. So we have 10 times Q. And then after we have 1/2 mv squared plus Q times the final potential, which I'll say is 0. So I said it starts out with 10 of potential and it ends up with 0. So what we would get is that the velocity is square root of 2Q times 10 over m, where Q is the charge of the electron. All right. So moving on to C. Points B and C are separated by a potential difference of 20 volts. Estimate the magnitude of the electric field midway between them. So I taught you that electric field is change in potential over change in X. The change in potential is 20 volts. The change in X between B and C is right around 0.01. So that would be 2,000 volts per meter. So I'm assuming that the electric potential, or that the electric field is uniform between those points. All right. D, on the diagram, draw an equipotential line that passes through point D and intersects the last 3 electric field lines. Or at least 3 electric field lines. So here's our electric field lines in the vicinity of point D. And here's point D. And one of the things I taught you is that the equipotential is perpendicular to the electric field. Okay? So the equipotential is going to kind of look like this. It's going to be perpendicular to those field lines. All right? Now, I haven't seen the next question yet, but I hope you guys are catching on. And you are going to guess that the next question is going to either have to do with circuits or magnetism. I think it's going to be circuits. What do you guys think? So let's go to the next. Oh, it's circuits. It's an RL circuit. Look at that. Oh my gosh. In the circuit shown above, resistors 1 and 2 of resistance R1 and R2 respectively, and an inductor of inductance L are connected to a battery of EMF E and switch S. The switch is closed at time t equals 0. Determine the current through the resistor immediately after the switch is closed. Okay, I'm going to flip this over. So if we close the switch, oh, you guys can't even see the whole problem. Let me scoot this over for you. Nathan Hoyle? What the heck is Nathan Hoyle doing here? Get off my stream, Nathan Hoyle. We've got an RL circuit, and when we close the switch, current is going to start flowing through the inductor. And inductors don't like the current to change. They say, no, 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 I don't like that current to change. So when we close that switch, the inductor is going to say, oh, no current for me. Because it doesn't like the current to change. Before the switch was closed, there was no battery in the circuit, so there was no current in the inductor. After the switch closed, the inductor isn't going to let the current just change immediately. So immediately after the switch is closed, the current that flows through the inductor will be 0. Okay? Which means that the current that flows through R1 will just be V over R tote, which would be E over R1 plus R2. Because if we remove the inductor from the circuit, because it's blocking all the current, then we're going to have a series circuit of just R1 followed by R2. Okay? B. Determine the magnitude of the initial rate of change of current in the inductor. So, basically what I'm going to say, so the current that flows through resistor 1 is going to then flow through resistor 2 when the switch is closed. Okay? So what that means is that the voltage across resistor 2 is going to be the current that goes through resistor 2 times resistor 2, which is going to be E over R1 plus R2 times R2. Okay? Now, that second resistor is in parallel with the inductor. So that's equal to L di dt, where this I is the current through the inductor. So what I would say is that di dt is equal to E R2 over L times R1 plus R2. Okay? Determine the current through the battery a long time after the switch has been closed. So a long time after the switch has been closed, di dt equals 0. Okay? Which means that the voltage across the inductor is going to be equal to 0. Okay? Which means that the inductor is just going to behave like a wire after a long time because it's settled down. The change has ended. Okay? So our circuit is going to be this. Where I've noticed how so the resistor R2 is right here, but the resistor R2 is short-circuited by the inductor because the inductor is just a wire now, so we don't have to worry about that one. So that means our current is going to be just E over R1. So that's the answer to part C. And then for part D, it says on the axes below, sketch a graph of the current through the battery as a function of time. So this is a little bit different because we know that the current is going to approach, oops, sorry, guys. Current as a function of time. The current is going to approach E over R1. And we know that the current starts at 0. Okay? So it's going to be an exponential rise to the final current value, like that. So this is, we talked about discharges where the current goes down, but this is actually charging the inductor. Okay? Sometime after steady state has been reached, the switch is opened. Determine the voltage across resistor 2 just after the switch has been opened. So, what does the circuit look like after the switch has been opened from an electrical standpoint? After the switch is opened, all we have is the inductor and the resistor. Okay? And the inductor is going to try to keep the current going because inductors don't like changes in current. So it's going to keep the current going in the loop. Okay? So basically, the voltage across the second second resistor is just going to be generated by the current that was going through the inductor. So here, when the switch was closed, the current went back to the battery. But now that this switch is open, the current can't go back to the battery, so what the current does instead is it goes up through the resistor. Okay? Because inductors don't like the current to change. They just keep the current going. But now what's happening is that the endpoint is changing. It's going through this resistor. So it'll be I times R2. And we know that the current that was flowing through the inductor just before the switch was opened was this. So we plug that in, and we get E R2 over R1. Okay? Boom. This is a 2-pager. CHL 421, Part 2. Knock it off! Hey, Bug, come here. Come here. Okay. So now we're going on to question 3. Question 3 says, ooh, look, a solenoid. A student performs an experiment to measure the magnetic field along the axis of a long 100-turn solenoid PQ, shown above. She connects the ends P and Q of the solenoid to a variable power supply and an ammeter as shown. The end P of the solenoid is taped the 0 mark of a meter stick. The solenoid can be stretched so that the position of end Q can be varied. So we're changing the L value of the solenoid. The student then positions a Hall probe. A Hall probe is just a magnetic field sensor in the center of the solenoid to measure the magnetic field along its axis. She then measures the field for a fixed current of 3 amps at various positions of the end of Q. Okay. And then it has some data. Complete the last column. Complete the last column by calculating number of turns per meter. So it's just going to be, that's really easy. That's just going to be, so this is question 3, part A. Let me see if I have some questions here. Oh, he's fact checking me. Okay. All right. I'll allow it. I'll allow you to stay. So turns per length is just going to be 100 over wherever Q is. So for example, for the first one, it would just be 100 over 40. All right. So that's going to be, what, 2.5 would be N. So that's the first, that's for trial 1. Okay. On the axes below, plot the measured magnetic field B versus N. Draw the best fit straight line for it. So I know what this data is going to look like because I taught you guys. The magnetic field for a solenoid is mu turns per length times I. So we're graphing magnetic field versus turns per length. So we can see it's a linear relationship. It's turns per length to the first power. So the data is going to look like this. Okay. I'm not even going to waste my time actually doing the numbers. From the graph, obtain the value for mu naught, the magnetic permeability of the vacuum. So basically, I have B equals mu I times N over L. So N over L is acting like X. B is acting like Y. So mu times I is the slope. So the slope of this is mu naught times I. Okay? So slope equals mu naught times I. And then it told us what the current was. The current is 3 amps right there. So I'm going to have whatever slope you end up getting is mu naught times 3. So that means that mu naught equals your slope over 3. All right. Continuing. D using the theoretical value of blah, determine the percent error. So the percent error is going to be the your measured mu, so mu measured, minus the actual accepted value, 4 pi times 10 to the minus 7, over the accepted value, times 100%. Okay? That's it for question 3. That was an easy one. All right, so something I want to point out, that was a 45-minute exam. I just did 45 minutes of exam in less than 30 minutes, and I explained it and I wrote it down. Okay, so I actually thought that one was a piece of cake. That free response. So I don't know about you guys, but that one was pretty straightforward. So I hope to talk to you on the Discord server later on. So I'm going to jump over to Discord right now, and have a great afternoon. See you tomorrow for more free response questions.